Yeah, okay. So David, why don't you tell us a bit about yourself and let's get into it.
Sure thing. Just share my screen here. Okay. Okie dokie. So my name is David Henderson. I work for the Australian Centre for Field Robotics, and I'm a mechanical and mechatronic engineer who's mostly does AUV design and operations. So okay, got it. So yeah, just a little bit of a sort of overall for today, do a bit of an intro, talk about what the Australian Centre for Field Robotics does, intro to our marine group, or subgroup as we say, excuse the pun, talk about engineering, my experience as an engineer at ACFR, and then talk about a couple of student opportunities. There's a RobotX student project coming up. It's actually open now for a part of it, and something that once you get back to uni, you're going to be able to get some hands-on skills and that kind of stuff. So finally, we'll do a couple of hints and tips from my time when I was studying, and then a Q&A at the end. So a little bit of history about me. I didn't go into university straight after school. I started doing, at school, I was really good at metalwork. I designed that slasher for our farm, which I'm currently at the moment. The slasher was for the front of a quad bike. It got me a really good mark in the HSC for industrial arts. And with that, I got an apprenticeship in electrotechnology working for a Navy contractor. So I did that for a few years. And then I moved on to a comms company that did RF communications for lots of different mission critical systems. So one of them was the Inner West Light Rail extension that went to Dulwich Hill or Marrickville. That was heaps of fun. I got to go to V8 supercars and do comms there. But after a few years, I got quite bored and decided that I would go to university. So I did uni part-time over 8 years, took ages, and it was, I probably could have done it a little bit earlier, but having some extra practical skills really helped me later. So I joined the UTS Formula student team, and we had a couple of really awesome years there. And then for my capstone project, which is a little bit different to your thesis because it's probably more of a practical bend, I designed, built, and did a design validation on a novel 3D printer. It's a perpendicular axis DLP 3D printer, especially designed for printing spiral-shaped objects. So from that, I got a couple of awards, which is really awesome icing at the cake at the end of an 8-year degree. And I won a few awards, including the EA's Engineering Student of the Year award. So that's a little bit about me. And then here's Steph. Some of you may have watched this video already, but I'm just going to play it now. So we do a bit of work with Engineers Australia, which is kind of where this comes from. I'm a member of the Young Engineers Australia Sydney Committee and as their uni and graduates manager. And so we organised this filmed session. So I hope you enjoy it. And this will give you a little bit of an overview about ACFR. Let me know if you can't see it properly.
Hi, my name is Stephen Williams. I'm the head of School of Aerospace, Mechanical and Mechatronic Engineering here at the University of Sydney. I want to welcome you to the labs of the Australian Centre for Field Robotics. Today we're going to show you a bit of some of what we do and share that with you during your break. I thought I'd start by introducing you to some of our agricultural robotic platforms. They're used to help farmers manage their crops and improve yields, to build better models of what's happening in farms. So this is RIPA. It's used in row crops where we have plants that are typically planted in a row. It's got a whole suite of different sensors and instruments underneath the hood here, so it can take measurements, build maps of the environments. It can even do autonomous weeding using machine learning to recognize the crop and weeds. It's equipped with solar panels, so it can run for 24/7 as required. It's got very high precision navigation instruments, so it can figure out where it is in the farm and conduct very long-term operations. So another one of our agricultural robotic research platforms is SwagBot. This one's designed for operating in rougher terrain, so in paddocks and things like that. We've actually used it to herd cattle, so it acts a bit like a sheepdog, but a sheep robot. We can also go out, take measurements of soil properties, deploy different imaging technologies to allow the robot to understand its environment, to get around. It can tow trailers and things like that. So it's a really versatile robot that allows us to go over a lot of different terrain on the farms. One of the things that we're particularly proud of is our ability to translate our research into practice. So we've had a number of startups that have come out of the Australian Centre for Field Robotics, including Agaris, which is one of our agricultural robotics spin-offs. They've taken a lot of the technology that's been developed in our agricultural robotics programs and have turned it into a commercial offering for farmers. They're looking at supporting sustainable practice in both small and large farms, and are one of 2 agricultural robotics spin-offs from this center. So this is another one of our robots that's used to support agricultural applications. It's a drone, well, amongst other applications actually. So it's a drone. Everybody may be familiar with the small drones you can buy down at the local shops. This is obviously a much larger drone, can carry much larger payloads, quite heavy cameras and other instruments. And we use these sorts of platforms to build maps of the environment. It may be on farms, it may be up on the barrier reef, looking at water quality. We do a lot of work also in the defense sector with these sorts of platforms. So this is one of our intelligent transportation systems test platforms. It's used to develop new autonomy methods for on-road applications. So we use this sort of platform to develop perception, control, and planning algorithms that allow these vehicles to operate on roads and around campuses. So my own research is focused on developing marine robotic platforms. So we do a lot of work with autonomous underwater vehicles. This is our AUV series. We've used this platform to document sensitive habitats all around Australia, looking at coral reefs, kelp habitats in the south, canyons, and have even taken it overseas to map ancient shipwrecks in Greece. So it's equipped with a whole suite of sensors, including sonar, high-resolution cameras, water column measurement systems, and we take all that information. It's all collected by the vehicle, and then we make that information available to scientists to help them better understand the marine environment. This one here is a smaller AUV, also an autonomous underwater vehicle, and it's used for collecting very similar information than our larger vehicle series. It has high-resolution cameras, acoustic positioning systems, and a suite of sensors that allow us to map the environment. We've actually taken this one overseas as well and have mapped ancient settlement sites in Greece. It's a 3,500-year-old city that was discovered on the Greek coast, and we use this platform to map that with a team of archaeologists. So this robot is an autonomous surface vessel. It's a robotic boat, and it's used for a variety of different applications. We use it for mapping the environment, for tracking our autonomous underwater vehicles, and we're currently developing some technologies that will allow it to deploy and recover autonomous floats to help us map the seafloor. Jackson and Will are 2 of my PhD students, and they're developing technologies for marine robotic systems. And one of the things Will is working on with a little startup in Sydenham called the Blueprint Labs is autonomous manipulation. So we've got a little grabber on this ROV. We're developing technologies to allow the robot to go and sort of pick up objects in the environment. So this robot's called Groundhog, and it's used as a platform for testing new perception algorithms and sensors. So at the moment, we've got it equipped with a radar system, lasers, infrared cameras, and we use that to map the environment and to help the robot understand what's around it. We've done deployments of this platform at Jervis Bay as part of a program called Autonomous Warrior, where we were doing demonstrations of combined air, ground, and surface vessel operations. So that's all we have to show you today here in the Centre's labs. We hope you've enjoyed the tour and really look forward to perhaps welcoming you to Sydney University.
Okay, cool. Any questions on that one? Feel free to ask away. You can unmute or put them in the chat. So I've had a few questions through in the chat. One thing that I mentioned was, like, most of the systems you just saw have some sort of development work being done on them. So there's always opportunities for internships if you know the person and the group that is looking after it. Yeah, it's good. Okay, so as far as the ACFR Marine group go, we're within the ACFR, but we actually have quite a different funding arrangement. So we're funded by IMOS, which is the Integrated Marine Observing System in Australia, and they manage all of the marine parks. So the purpose of us being IMOS's AUV facility is that we do field trips and we collect data of benthic environments, which is, as you can see down here, so temperature, salinity, dissolved solids, but probably primarily benthic imagery. So as our subs will dive off the side, well, we'll launch them off the side, sometimes with great difficulty. It'll then track down to 2 meters above the ocean floor, and you sort of mow the lawn and take lots and lots of photos. So for a standard, say, 2-3 hour dive, we might collect between 20 and 40,000 stereo pairs of images. That allows us to, in the case of a new reef or an area that's just been made into a marine park, it allows characterization of the reef. So they go, okay, what percentage of coral cover, what particular species of coral, what animals are there, what kelps are there. And that's really useful. And then other trips we do are sort of follow-up trips, which I'll show you an example of later. And that allows us to capture the same interest areas a couple of years later, and then we can sort of see changes. So increasingly, there's sort of machine learning used to, for example, go through a huge data set of images and find, a crayfish here or a crown of thorns here. And through that, I guess this is called quantitative data analysis rather than qualitative. So the advantage is we go down to, say, 200 meters, 250 meters, and spend 2 or 3 hours down there, which is something that divers can't do. So using these AUVs really open up the ocean floor to heaps more research. 80% of our ocean is totally unmapped. So there's heaps more that we can learn from that. And we want to take good care of it. So here's a site map and also a Instagram thing if you want to follow our work Instagram. So these are the different sites that we have done AUV deployments at. And as you can see, 6.8 million images. You don't want to be the person who has to go through them all yourself. So that's why we need young, bright engineers to develop intelligent machine learning algorithms to do that for us. So yeah, so you can probably scan that QR code off that and join our ACFR Instagram. I'm running it at the moment, so it helps me if we get more followers. So here's an example of a repeat site. So this is at Lizard Island. Now, there was a big bleaching event due to a heat wave / climate change. There was also a hurricane at the same time. Shallow reefs get knocked around really badly by hurricanes, so it actually breaks them all off. So you can see here in 2010, lovely healthy coral. Same time the next year, horrible bleached, nothing yet alive. And then 3 years later, 2 years later, you see all these little corals starting to grow and they get bigger and bigger. It's quite amazing to see how they recover. And it's something that doesn't get talked about very much, actually, is, what's the best way to help reefs recover? And, this is the data that we collect is helping scientists understand that. I might just pause here for a second. Does anyone have any questions before we get in there? And I don't think I can see you, but I can probably hear you. You can hear me all right?
Yeah, we can hear you. All good.
Yeah, perfect. Okay, cool. Feel free to just unmute and ask questions. Get you ready for actually face-to-face learning at some point. So it'll be good. I'm really looking forward to coming back so that I can actually see people in real life, because I understand it's a pretty bit of a struggle. So on our team, so a big a big part of what we do is actually collecting the data, but to do that, we actually develop our own systems. So there's two systems here that we've developed in their entirety. So Nimbus up here, this is the torpedo AV. It's about 130 kilos and 3 meters long. It's fairly recent, in the last 6 years. This large sub over here, this twin hull, is called Sirius, and it's just turned 16. So it's a veteran of lots and lots of campaigns. It's been lost. We've lost it for a couple of months before, or a couple of weeks before. I've nearly lost it myself when it got caught in some rope in a very rocky reef. Luckily, we were able to recover it. And down here, this float, bottom following float, they're called, is our sort of new generation of cheap sort of AUVs, I guess. So both of the top, both of these platforms are powered up, down, transverse, and they will go and do a predefined route under the water. It's usually like a Z shape or something, or a square Z shape. Whereas this float down the bottom is novel because it actually doesn't propel itself at all transverse. So it only controls its altitude. So the idea with this is we get the WAM-V that you saw beforehand, and is also the subject of the student project. And we'll drop 4 of these off over an area of interest, and they will float over the top with the current. So this allows us to sort of collect a lot more data a lot cheaper, because these things cost maybe $15,000, whereas Sirius would be probably $500,000, and Nimbus would be, I don't know, $400,000. So this will allow us to capture more, use much smaller vessels, and cheap data is great for science. So the more data we can collect for the unit cost, the better. So in our team, we have a core team of Christian, who's our electrical and team lead, Lachlan, who does software, myself, I do mechanical and mechatronic, George is mechanical, and Brenton does his mechatronics degree, but does lots of software. So we work together, and each of us has our little sort of specialist areas. But when it comes to field trips, we're all expected to get in there and do it. So here's some examples of some of my work at ACFR. So on field trips, you'd be out in the ocean for, say, it's usually from a week to 3 weeks. And it's quite an adventure. It's really adventurous. You can have really rough seas. That, as you can see here, this boat is swaying a fair bit as we're trying to bring Sirius back in. 260 kilos hanging off a crane can be a bit of fun if the swell's up around 2.5 meters. Anything over that, we won't bother. This second picture here is Nimbus, and this is in a prototype launch and recovery system. So I built this in a week in Tasmania to safely, or more safely, launch AUV Nimbus out of the back of this boat, which is owned by one of our partners, UTAS and IMAS, which is Australian Marine and Antarctic Studies. So this actually pivots up, and then sort of telescopes out and allows us to launch and recover a lot safer than having a large torpedo swinging off a crane. So this picture here is a design I'm working on at the moment, which is an updated version of this. I had to iterate this design because this doesn't fit in the travel case. So this doesn't telescope, but it folds up, and it allows, once it's all folded up over itself, it fits in the box. It also has lots of different ways to configure it to suit different freeboard heights, which is the height of the boat's deck above the water level. So all of these things are important, interesting sort of design considerations that we have to make the most of, because we don't have our own boats. We're always operating on other people's boats. So depending on the boat availability, we might have 6 field trips and use 6 different boats in a year. So this is another design down here, which is a USBL, universal USBL pole. So this transducer here is sort of an underwater pinger. So while our subs are underwater, we get like very sort of, low bandwidth comms available. So this pinger will send and receive packets of data that will let us know what the status of the AUV on the ocean floor is. And it will also give us a approximate location, which then we can send back fixes to correct the movement on the seafloor. So this is designed to hinge up and out of the way because these are very sensitive, and you can't, you're not supposed to run them while they're in the water if there's any sort of water or turbulence, or if they're close to the waterline, because it can damage the transducer, and they're about $30,000 each. So this one will pivot up and then slide inward and can be set up in lots of different configurations, either side or rear mount. So picture down here, this is a picture of Nimbus's nose. Nimbus is this sub AV up here. I had to redesign it for extra strength because of how we launch and recover it using this LRS. So this is a bunch of new parts. It doesn't look nearly as shiny anymore, because these things get banged up a bit, but we patched them up and put them back together. That's one of the most challenging things about when you're on a field trip. If you're 600 Ks out in the ocean, you can't do a quick run to Bunnings, or you can't do a quick run to JCar. So if something breaks, you have to fix it there. So we take we take good spares kits. So this picture is the WAM-V, SS George Michael, and the WAM-V is an autonomous surface vessel. So this will be the subject of what I'll talk about later with the student project. So it's been since it last went to competition in Hawaii in 2018. It's sort of been in pieces. So a big job of mine over the last year has been to get it all back together and document it really well, so I can hand it over to the new RobotX team, and they will have, you know, a good base to work with. Okay, sorry, I shouldn't have read the comments as I'm going. MC can moderate those. Now, this is the last picture. This is one of the biggest field trip I've ever been on. 3 weeks in the Coral Sea to map some brand new reefs. It was on a boat owned by the Schmidt Ocean Institute, which is the CEO of Google's sort of philanthropic effort. And so he makes this boat available to go and do research. So we signed up to be part of that. And this is me giving a toolbox talk before we do a sub launch. And in the back, you can see there, that is a very large ROV called Sebastian. That's 3 tons. It can go, I think it has a 7-kilometer tether on it, and it can go down to 4.5 Ks deep. And this was really useful because at one sea mount, which is kind of like an underwater mountain that doesn't actually breach the surface, we got Sirius over here decided to have one of its, we suspect a gearbox failure in the vertical thruster, and it actually got stuck, and it got stuck at the edge of a 1.5 K cliff. So we actually got we got that AV to go down and actually pick it up, and I wrote a blog post about it. It's on the Facebook event thing. Any questions? No questions. Okie dokie. So one of the challenges of being away for a long time is sometimes you get beautiful conditions and you're like, this job's awesome. Other times you get conditions like this. So this was on our way back from Elizabeth and Middleton Reef, and that's about probably 600 Ks offshore in line with Coffs Harbour. And we had to leave a couple of days early because we got chased down by a cyclone. So we had 48 hours of these conditions on the way home. And yeah, we were pretty glad to be back on land. Arrow keys don't work properly. So recently there was a story on Catalyst, and this is like an excerpt of it. So Steph Williams, this was down in Tassie. So I'm going to play this and you can have a look at, it's the best footage I've got of Nimbus in action.
Yeah, so it's bringing in a little bit of air just because it's on the surface.
It's definitely giving me Bond villain vibes.
Oh yeah?
Yeah.
So right now it's transiting over to the actual site where we program it to dive. Then it'll dive down 2 meters off the sea floor. That's where we get good imaging.
As Nimbus autonomously travels along the seafloor, it captures every feature of the hidden world in incredible detail. Then the images are stitched together to create a comprehensive, kilometre-long 3D map. It's hoped that entire fleets of AUVs like Nimbus might one day be used to map and monitor our planet's marine forests, helping scientists protect what's left. But is there any way to restore?
Yeah, so it's
Cool. So that was Nimbus in action. So now we're going to move on to opportunities for students. So when we had a look back at that autonomous surface vehicle, the WAM-V, the reason that we actually got that is because it's part of a student competition. So it's RobotX is a competition that is a international university-based competition where students get together and make an autonomous surface vehicle, do a whole bunch of different tasks. So you'll have, I'll talk about the full range of tasks later, but in the meantime, because we're not allowed to really do very much now, it was decided to do a virtual competition. So what we're keen at, what we're keen about at work is to get a team of keen students together with our support to build a team and then compete in this virtual competition. So, and all of the stuff that we learn in this competition will hopefully transfer to the physical competition at the end of next year. So this is actually just opened. So there's a whole bunch of documentation, there's Git repo, and there's heaps of stuff involved to do. But we're really keen to just actually rebuild the team. So we had a team, and unfortunately, with all of the lockdowns over the last year, it's been really difficult to maintain it. So we want to get some fresh blood and also existing blood, I guess, over as well. So yeah, team building. Okay, so if you like, I can send a bunch of links, and I'll probably also give you my email in the chat so that you can, if you're interested in this, you can send me an email. So an example of what to do: station keeping. So station unmanned system capable of localizing and fusing sensor data to maintain the position. So this is really important, for example, is if you are, for example, geez, I said that a few times in a row. If you're in a rocky boat and you have to either shoot a target or pick something up where the boat's motion is different to the motion of whatever you're trying to pick up, or say an enemy boat, you have to know how to be good at station keeping. This is also really important if you're, for example, trying to dock in a specific location or navigate whilst there is a 10-knot wind and heaps of waves. So this is a basic part of any sort of autonomous vehicle operation in the water. And from that, all the rest of these are built. So, okay, using all the different sensors, add to cameras, LiDAR, acoustic receiver. There's heaps of hyperspectral camera stuff to do on this. I've never done anything with hyperspectral cameras. So it's a really cool, if you got involved in that and became a subject matter expert on hyperspectral cameras, I think you would have no trouble finding a pretty serious job almost straight away. So this is a really good opportunity. So as part of, with the sensor package, you have to be able to recognize different buoys, markers, obstacles. So if you know anything much about marine stuff, you'll notice that there's green and red buoys. They're usually like a channel marker to say, if you're going to travel past this, travel on this side of it. So another important thing to do with, especially when you work in a job that is somewhat about conservation, is encountering wildlife and not running it over. So we don't want to do that. So there's a challenge for that. More applied tasks that'll show doing more different sort of complex actions is to find a pinger in a field of obstacles. And in the actual physical competition, I think there may be a pinger on the bottom of on the ocean floor, and then it'll require launch of a remote operated vehicle as the ROV to go down and pick up the pinger and then bring it up and then get back to the exit. So it's quite a challenge, but you know, teams managed to do it. It's really, really cool. When I was doing uni, there was nothing like this on offer. So it's really good opportunity. So then next year, October 2022, it's in Sydney, they're going to have it. It's international university-led competition. ACFR and Talus are going to support it for our team. So we've got a fantastic amount of backing. There are lots of different tasks to do within the challenge, from hardware, software, camera stuff, machine learning, object detection, all sorts of things. So if you're interested in anything and you want to do, have something amazing to put on your, your resume and build friends and awesome. I had so much fun at university myself, being part of the Formula student team. Not saying you should, you definitely join that if you want to as well, but this one should be fantastic. So being able to build a team and learn heaps of skills, especially hands-on skills, time management, people skills, great. So here's a video of the competition that's going to be next year. It's in Sydney instead of Hawaii, but it's a fantastic opportunity and it'll be close by, so we'll probably get lots of time to practice.
G'day and welcome to Sydney, Australia. Your destination for the International Maritime RobotX competition in 2022.
The event will be hosted at the Sydney International Regatta Centre by RoboNation and Australia's Defence Science and Technology Group, funded by the Next Generation Technologies Fund.
The university teams from the Pan-Pacific region will convene right here to test and demonstrate their autonomous maritime systems.
Like in previous competitions, teams will use the WAM-V, which provides a unique stabilised platform. Teams will have to autonomously control their WAM-V's propulsion and navigation and develop complex visual control systems through machine learning and image processing. This year, teams will have to incorporate an independent UAV and apply hyperspectral imaging techniques to navigate and complete the challenges.
I think RobotX is an excellent opportunity for women in STEM. As far as I know, there aren't that many maritime events comparable to RobotX in terms of scale and complexity. So it's a great opportunity for women engineers and the students to get out there and get some hands-on experience in that competition.
I'm currently completing my Mechatronics engineering degree whilst working with the Royal Australian Navy and Defence Science and Technology Group. RobotX is definitely the Olympics for autonomous maritime vehicles.
Things like RobotX create a lot of interest in this technology and the applications of the technology, and it gets a lot of young people excited about it. And for companies like OCS, it's an opportunity to find those sort of people that we can actually then ask them to come and join us.
My advice for students considering entering RobotX is that if you have that opportunity, take it. I met some great people. I got to play with some very expensive and very cool equipment, and travel overseas, and it was great.
I'm so excited that my university is a part of this competition, and I look forward to participating in 2022.
So if you want to be part of one of the most advanced international robotics competitions around and develop your autonomy skills at the same time, email us at the address below.
Cool. So any questions on that?
This is more of just a general question about, navigating in the marine environment. What do you find, like, what's the biggest challenge you find, mainly, you could say, with avoiding like obstacles, that kind of stuff, like just navigating yourself around the actual environment itself? Like, there are any main issues there?
Yeah, so some of the main issues you face is we're often flying blind with regard to what the currents are doing. So there's no really good way of measuring currents underwater. You'll often get especially around obstacles. So if you have a nice clear stream and you have somewhat laminar flow, well, it's never quite, but close to. On the surface, the currents can be doing something completely different to what is happening underwater, and especially around obstacles underwater. So it can mean that you drop it off, and as the sub comes down, it drifts one direction and then drifts the other direction and then drifts the third direction. So it's really tricky for that initial localization to know where it is on the ocean floor. We use USBL to help, but it's never perfect. As far as avoiding things underwater, so we use OAS sonars for that usually, obstacle avoidance sonars, which will send a ping, and you know, the logic behind them isn't, it's not super good. So it'll pretty much come until it senses something close, and then it'll sort of lift up and go over it. The problem is it can't go in reverse. I'll have to finish my water first at the moment. So sometimes it'll find a cave and it'll go, uh-oh, found a cave. What am I going to do? Nothing. And then it'll time out, and hopefully it'll drift its way back up. But sometimes we'll have to go and recover it, which is always scary because you don't want to be the guy who lost the submarine. So any other questions? Yeah?
Oh, sorry, I keep going. How come you can't reverse? Like, is there any reason why?
Oh, we can totally reverse. It's just not part of our code at the moment. The code is also always, I'm not the right guy to talk to about this, PS. I'm the mechanical guy. I can put you in touch with the person who would be better at explaining this. But at the moment, we've got lots of different other priorities, and it works pretty well. We barely ever lose it. Well, we don't really ever lose it because of not being able to reverse, but it's something that is in the timeline of stuff to develop. Did I answer the question badly?
No, yeah, that's good. That makes sense.
Good. Okay, so here's a quick video of, this was the maiden voyage of SS George Michael. At the moment, it's just been fitted out with a whole extra undercarriage here to actually pick up floats, be able to run over them and pick up the float subs. It's quite a piece of engineering. But here is, yeah, one of its first little runs out. This is we have a test facility at Chowder Bay, which is near Mossman, which is fantastic because it allows ourselves and also students, we had a couple of interns working on this as well, to go out and actually get their feet wet, literally. So, and it's actually really fast and quite maneuverable because you can have the props going different directions. It can pretty well turn on the spot. So yeah, so because this is actually built and running, it's a huge head start for the team in 2022. Okay. Internship opportunities. This is Rachel over here. She was from UTAS. She came to do an internship. She's working with some previous members of the team putting batteries together. We have lots of interns. We recently just had one that helped us make new drop weight fuses ourselves. So a drop weight fuse is a piece of magnesium that is designed to corrode at a set rate in order to drop some ballast on the AUV to make it more buoyant, so that after the longest expected time that the AUV is supposed to be in the water has elapsed, it will actually corrode, drop a 1.5 kilo weight to make the sub more buoyant. And if it's stuck somewhere, well, hopefully it will come back up at that point. Sometimes they get caught up in things, and all sorts of things can happen under the water. So many unknowns. So yeah, so she worked on the WAM-V team. There's lots of opportunities for summer internships. I know we have a fair bit of work to do at ACFR and in the subgroup. So if you are keen, I will get the contact details and I'll put them in the chat of who to contact for that. Is anyone keen for opportunities? And when do you actually have to do them? I went to UTS, so it was slightly different. It was like middle of second year we had to do an internship, but I know your PEP system is different. Can anyone answer that?
You just have to get hours throughout your entire time at uni, basically. So you have 3 stages and you just have to get hours every semester. Yeah.
Oh, okay. And does the internship count as that?
Yeah, so towards PEP 3, you need work experience. So I think this will count as working engineering experience.
Okay, fantastic. So when does PEP 3 usually occur?
I think towards the end of second year, I want to say, or start of third year, maybe.
Okay, yeah. Well, that's probably really good timing to do an internship at ACFR. So you've got a little bit of knowledge, and you probably make the best use of it. I wouldn't recommend going straight in at the start of first year or anything like that. You learn more if you've got the basics ready. So I've done a few of these talks, and I had some times in my uni career where I struggled a bit. So I developed a couple of techniques to help. And then it kind of depends on what kind of learner you are, but I found it really helpful to find real world applications for what you're learning. So if you're doing thermo, apply it to, I don't know, your favorite fast car or something like that. If you're doing fluids, you can apply it to, I don't know, pretty much find an application that you're interested in that is a place that you'll learn that, well, that you will use those skills. And then if I have an application, I found it so much easier to remember. So that's number one tip. Bend your uni work into your interest areas, especially for your thesis. I think a lot of people start doing a capstone, a thesis, or doing something that they're not totally interested in. Not saying that you have to only choose it on your favorite thing in the world. You can't do a thesis on eating pizza and playing video games, as much as that would be awesome. But if you find something out of your interest area in engineering, or any favorite lecturers that you had that you felt were really good, ask them. They'll put you in the right direction. And it makes a huge difference, because ending with a bang is a really, really good feeling. Another one, get involved in external projects like this one. Learn and practice soft skills, super important in the workplace. Yep, often neglected. I'm still working on mine a lot. Speaking publicly is one of the reasons I do stuff like this, but also trying not to be a pain in the ass to all your workmates is a big part of having success at work, something I don't always achieve. Next one, build and develop hands-on skills. Yeah, make a project, fix the car, push bike, pull something apart, is great. You can learn a lot by pulling apart a washing machine on the side of the road. And also you'll have heaps of different parts that you can use. Printers are another good one that you can pull apart. It'll make you a better designer, I've written there, because when you pull things apart, especially cars, and you go, why did they do it like that? It makes it so hard. So that's part of a good design mindset, is to design for manufacture and also design for maintenance. So engineering events, especially, like I feel really sorry for especially first and second year students, but all of you guys actually, because I found the social side of university so important, and you guys haven't had any of that for like a year and a half pretty well. So I really do feel for you, and I can understand there's heaps of students feeling pretty despondent at the moment, but lots of events are being held, and as soon as everything opens back up, I'm sure there's going to be a flood of events. So get out there and get back into, relearn how to socialize. I'll have to do it too. But face-to-face social skills are fantastic, and yeah, get back into the swing of things, do a bit of networking, and so you can complain to all your other friends who've had similar experiences, and that's cathartic. Then the last one is to have fun, because it'll be over before you know it. Sounds kind of pithy, but it was certainly, yeah, I don't know. Stockholm syndrome might be a thing, but I quite enjoyed university at the end. So yeah, enjoy it. Once you're in the actual workplace, it becomes even, yeah, just the next grind. So anyway, questions. I'll stop sharing my screen so I can see your faces. Oh, alrighty, any questions? Have I put you all to sleep, or was it okay?
What did you find was the hardest transition going between university and saying working at ACFR?
ACFR, yeah.
ACFR.
It was different for me because I had worked part-time the whole way during my internship, I studied part-time. So that was different. But I found the transition from working to studying to be the hardest. I had to learn how to study. And then going from uni to work, I think my biggest challenge, was I'd learned so well to work in a structure and to have like set deadlines and stuff like that. Whereas when you're in the workplace, you may or may not have that. And time management is something that I'm working on, actually, to try and give myself deadlines and make sure that I'm on track and prioritize things. So, and project management, which I'm going to sort of dip my fingers into soon. I found that really hard. Anywhere else? Anyone else? Feel free to speak over me or each other. I don't care. I'll answer as many as I can. We're 10 minutes.
I had a quick question. I remember just before you were going through like who's in charge of, well, not in charge, but who primarily does software and who primarily does electrical and mechanical and stuff. And I think you said you were primarily mechanical. Is that right? You were like in charge of that area?
Yeah, I do. Well, we've just got a new mechanical guy and we've just lost a software guy. And there's only one guy doing electrical. So I'm actually in the process of moving into more mechatronic stuff. But all the WAM-V, I've got a background doing sort of mil spec wiring. So I'm going to be doing lots more of the sort of mechatronic side of things. But I have been primarily mechanical and operations up until now. But I did do all the electronics and electricals on the WAM-V.
Right. So how hands-on is the mechanical side? Like, are you, designing and actually manufacturing parts and things like that? Or do you mostly outsource it and just sort of design it and then put it together afterwards?
So we've got a few different ways that we have stuff built. So small stuff, we do heaps of 3D printing prototypes of things. And a lot of the parts we use on the subs are 3D printed. And that's because it's super easy to replace them and you can make complex shapes fairly easily. Other stuff, any big expensive stuff we'll outsource and we'll do the design and we'll either outsource it to the AMME labs at University of Sydney. So we have, part of the job is to have good working relationships with all the guys down in the workshop. And then anything that's out of their comfort zone will go to an external person, external company. So things like getting stuff hard anodized, having complex machine parts made that require sort of like 4 or 5 axis CNCs, that stuff will usually get outsourced, or stuff like, laser cutting and stuff like that, which is, a lot cheaper to do at a specialized laser cutter, we'll outsource. But yeah, we design, prototype, build, put it in the sub, see if it works, iterate it, done deal. We do the whole lot. That's one of the cool things about the job, actually. You see the whole process from start to finish.
Oh, cool. Also, do you know if like in the AMME labs that, you sometimes get them to build stuff, do you know if there's opportunities for students to be in there, like helping building parts, or is it like dedicated technicians and like people that are just in there full time doing it?
Yeah, they're professional staff there. There are different things that you can get involved in that might do that. If you're interested in building machine parts and doing stuff like that, I would say the Formula student team would be a good one because they're right next door to them. And I know they do a lot of work together. So they're pretty much under the same roof. So
okay.
If that's why you're interested, if you've got an interest in manufacturing, that's a good thing to volunteer for.
Awesome. Great. Thank you very much.
Welcome.
David, we got one more question from Rebecca asking, the boats had some fun names. Who's responsible for that?
It's usually whatever team was there at the time. So we've got Sirius and Nimbus. We've got Iva, which was purchased, so that's its name. We've got the float sub, or was originally colloquially called Sea Wang. And yeah, so we come up with them ourselves pretty well. So we try and be good and not name them too catastrophically, but yeah, we'll see. We have a bit of fun. Got to have a bit of fun.
Great. One more question I had is, how much say would an intern with AFCR have regarding major design choices in the vehicles?
If you can justify your design choice, and we can all see that that's a good way of doing it, we'll say heck yeah. If you have like, you say I should do it like this, and then you can't back it up, well then you've got no hope, and you'll probably be pulled apart mercilessly.
So yeah,
well, not like within fun. Like it's easy to come in and go, oh yeah, you should probably do it like this way, and it's like that's when you got to learn those social skills, learn those soft skills.
Yeah, definitely.
Yeah. So another question: what happens when something goes catastrophically wrong? Well, it does go wrong. Sometimes it goes really badly wrong. So we've lost Sirius once for 2 weeks and washed up from Moreton Island to Noosa, and we got it back, luckily. I've personally got serious caught in an anchor rope. Well, I didn't do it. We've had housing split as they come out of the water and have a little bit of water in the battery compartment, which is not where you want salt water. But it is part of it. And something I'm really impressed with my supervisor, Christian, who's the team lead, is how calm he is when everything goes to shit. So there's a certain amount of marine operations that you have. There's a little bit of just like, okay, how are we going to get out of this? What are we going to do? No one freak out, because, you know, things are bound to happen when you chuck $500,000 worth of electronics into salt water. So, yeah.
On that note, because they're so expensive, do you still have to like have someone monitoring them the whole time to like check everything, or is it completely autonomous and you can just kind of sit back?
No, okay. I had a video for this. So while it's underwater, we're monitoring it constantly on the laptop. So it'll send back its ping positions from the USBL. So constantly monitoring to see if it's doing the right thing. And if it stops doing the right thing, then we need to probably take action in some way or another. And that can be just like aborting the mission and having it just come back up to the surface. Yeah. So it's always monitored. It's always monitored. If we can't see it on the computer screen for, like, I don't know, you might lose it for 4 or 5 minutes or so. If it's say behind a cliff or something and you can't get good comms to it. But yeah, usually, yeah, there's always somebody watching it.
Yeah, cool. All right.
Okay. So I'm gonna send out the attendance link for everyone who wants to claim their PEP for this now. So there it is in the chat. Feel free to fill it out, but definitely don't be afraid to ask more questions and keep the talk going. I'm gonna stop the recording now though.